Yeah, good afternoon, everybody. Let's start the class. Okay, morning we are saying about this one simple distillation or differential or radish distillation. So, in this distillation technique, since this is a simple distillation technique, a known quantity of a liquid mixture is charged into a jacket or this still, whatever this still is there. In this one, a known quantity of liquid mixture will be just charged. Then the jacket will be provided with a heating medium, like steam will be provided in order to heat the content inside that still. Then after some time, the charge will be boiled slowly. Then vapors will start to boil. Yeah, after some time, the liquid charge which is in the still will be start to boil, and the vapors will continue to continues to form. As soon as the vapors are formed, it will be just taken out from the top and it will be sent to the condenser, in which a condenser using the cooling inlet and cooling water outlet, the condensate, whatever the vapors are there, it will be condensed and it is collected as a condensate in the respective distillate receivers. So the receivers are labeled as R1 and R2. We will call this as a cuts, distillation cuts. Since this is a batch operation, okay, at the same at one temperature and at one time, only one cut of vapors will be possible, and that cut will be sent to the receiver one. And at the second time, the next cut will be sent to the condenser and then condensed and will be received in the receiver. So the composition usually during the initial time when the vapor starts forming, the concentration of more volatile component in the vapor phase will be very more, because since this is a more volatile component or which has a less boiling point, because of that one the concentration of the more volatile component in the vapor phase will be very more. So the first initial receiver, the initial condensate which has been received in the receiver will have obviously have a more amount of more volatile component. As soon as after some time, whatever the vapors are forming will become a lean in the more volatile component, and the less volatile component will comes to add. So when we increase the temperature furthermore and we increase the time and we give the enough time, so all the liquid inside the steam will be gets vaporized. Those vapors during the initial time, the more volatile component in the distillation cut, simple distillation cut will be very high. And as the time passes, the more volatile component will be lean in the distillation cuts and the less volatile component will be more. So we will just do this operation, simple distillation operation, until certain set point of boiling temperature, or otherwise until the certain composition of liquid has been received in the receivers. Okay, whatever the set point may be, we will fix the set point initially, whether the particular liquid has to vaporize up to certain volume or particular liquid has to heat it up to certain temperature. Okay, whether it may be temperature or whether it may be a volume of the liquid to be vaporized. Then we will start the distillation column, distillation operation. So the overall operation is known as a simple distillation operation or a differential distillation operation or a Raleigh's operation. Since the cut, initially the cut in the receivers, the concentration of more volatile component will be high. And as the time passes, the concentration of more volatile component will be lean and the concentration of less volatile component will be high as the time passes. So the average composition needs to be taken out. Average mole fraction of more volatile component needs to be taken out, because the concentration will be different, depends on the each cut, at what temperature we are eating, at what volume, what is the volume of liquid which is getting vaporized. So the feed inlet, this is a feed inlet at which the feed flow rate is denoted as F, and feed concentration of more volatile component in the feed is this one, mole fraction or the mass fraction of more volatile component in the feed is XF. So since in the distillation operation, largely we will denote our notations with the mole fractions and molar rates. Okay, we don't go for the mass fractions. Okay, we can also calculate this for the mass flow rates, but usually we use mole per second or moles. Since okay, then concentration of more volatile component, mole fraction of more volatile component in feed is XF, and mole fraction of more volatile component in residue Okay, distillation has one input and two outputs, and the one first output will be a distillate whose molar composition is D and whose mole fraction is YD average, because the concentration will change. The mole fractions will change in the respective cuts. Because of that, we are taking average. Then in the residue, the moles of residue formed will be W, and the concentration or the mole fraction of more volatile component in the residue will be denoted by XW. So where do this simple distillation finds application? So this simple distillation will find an application in removal or purification of many organic liquids. Okay, this distillation will found, since the organic liquids will have the large temperature difference between water and organic liquids. So simple distillation can be used to separate these organic liquids. Then separation of liquids from non-volatile solids. Okay, in the evaporation, according to the definition of evaporation, what is evaporation? Nothing but a separation of whatever the volatile liquid is there, whatever the volatile solvent is there, that must be separated from the non-volatile solute or a solids, we can say. So in the evaporation, these two are neglected. Only one still is present. So next is preparation of ether, amyl nitrate, and spirit of nitrous ether. So in the preparation of these compounds, the simple distillation can be used. Since they are not a complex one, they are not at all forming azeotropes. So separation will be very easy. So because of that one, simple distillation will be very helpful in separating those components. Then the simple distillation is used in preparing distilled water. Since salts do not have any boiling point, so separation of salts, the dissolved salts in the water, will be very easy using the simple distillation. Whatever the vapors will be formed is a pure water. So it will be condensed and the distilled water will be collected in the receiver. Therefore, this distilled water finds many application in the laboratory experiments, etc. Okay, then this is about the simple distillation column. So in the simple distillation column, Rayleigh, one author who is named as a Lord Rayleigh, okay, so he derived the equation, this assuming the differential approach. Okay, what does that mean? A differential approach. Okay, using the differential approach, he just provided the mass balance or a mole balance for the simple distillation column. Then what does this mass balance with a discrete approach or the differential approach? We will see this one. So how to derive this? This is called a Rayleigh's equation. How to derive this equation? We have to see this one. For example, consider if this is a still. I am using different color. Okay, since this is a simple distillation column, for example, there is no input and output during the operation. Okay, that means a batch operation. This is, if you consider this as a still, in which initially we fed L moles of liquid into it. Initially, the L moles of liquid will be in this still, and after some time, what will happen when we heat this? When we apply heat to this operation, what will happen? That L moles of liquid will be appeared as a vapors. Okay, due to we are applying heat. So this vapors will have some composition of differential amount dl. So dl moles of liquid will be just vaporized, and after some time what will happen? We just given these vapors to some condenser. Okay, these vapors, this whatever the vapors are forming, the differential amount of vapors, we are giving these vapors to the condenser at time. This is at time t is equal to 0, this or at time t is equal to 0, time t greater than 0 or t greater than 0. Time t greater than 0, these two operations will take place. We will supply this to the condenser. Then what happens? This overall vapors will be condensed and condensate will be formed. That condensate we are denoting a differential amount of distillate. Okay, let's say this is a differential amount of distillate and this is DL. This DL only, it is going to the differential amount of distillate. Now what happens? Now if you see, apply a material balance or a component balance around the distillate. What happened? Input moles of liquid is equal to output moles of liquid and vapor. So if you see input, initially what we have provided input, L moles we have given to the still. Distillation still we have given L moles. Then the output, it is appearing as, so initial inputs are there. Then whatever the outputs are getting, DL amount output is getting. So the amount of liquid which is left after evaporating DL amount of vapors is D minus DL. So this amount was already evaporated and this evaporated liquid has appeared as a distillate here. So this is plus DD. After some time, this evaporated whatever the liquid evaporated DL is received here as a distillate. Now just applied a material balance. Now we will cancel out the terms. L is equal to L minus DL plus DD. So L on the LHS side and RHS side we can cancel. So the left out will be this one, DL is equal to DD. Okay. So I just explained you the same one. Whatever the DL has been coming here, the vapors will be sent to the condenser and it will be received as a condensate or a distillate here. The same approach we have shown through the material balance. Now this will be equation 2. So this equation, if you assume the mole fraction of more volatile component in this L moles of liquid will be X. If you consider mole fraction of mole volatile component in this liquid as X, and here similarly dx amount of liquid will be vaporized dx amount of liquid will be vaporized, and this will be, since these are vapors which are condensed, these are denoted as Y. Okay, then if you apply a component balance for the more volatile component, okay, this is overall balance. Then if you apply component balance for more volatile component, the same one, the input is L, for the more volatile component it is X. Then L minus DL moles are already left in the still. Then with respect to L, the concentration of more volatile component is X. And with respect to DL, the composition of more volatile component in DL is dx plus DD amount has been found as a distillate. Then the composition of more volatile component in the distillate is Y. So this will, okay, this will looks like it is also differential. Y is also, so Y is not in differential. So Y DD we can write. So now let's expand this one. Lx is equal to L into X minus L into dx, then minus X into dl, then next one minus minus it will be plus dx dl plus, and the left out is Y into dd. So Y into dd. Let's cancel out the terms. LS and LX. LX and LX. Then the left out will be this one is equal to 0 minus LDX minus XDL plus DX DL plus Y DD. So this is plus YDD. So if you see, the amount of liquid is there is L, and the amount of liquid which is vaporized is DL amount. So at any point for any single cut, this will be a dx amount of more volatile component is vaporized. So this dx and dl, the what we call the product of dl and dx will be very less for a single cut. I am saying not for the whole distillation column. For a single cut, the product of DL amount, differential amount of liquid vaporized, in that one the more volatile component composition will be very less. So we will take this as 0. Then the left out is, we will send this to this side. So L dx is equal to minus, okay, we will write y dd plus x into dl. X into dl.
Minus no sir.
Yes.
Sir, minus XDL.
Minus. Okay, sorry. This is minus xdl. Then this equation, we have to give equation numbers. This will be 3, and this we will give as 4. Then the LDX is equal to YDD minus XDL will be left out. Then from this one, what we have to do, we have to just take from equation 1, from equation 2, I guess, yeah. From equation 2, we have just proved that DL is equal to TD. So this fact we have to substitute here. So L into dx is equal to y into dl minus x into dl. So now we will separate the common variables is equal to dl, we will take common, dl into y minus x, l into dx, and we will bring this to dl to this side, and we will send this dx to that side. Okay, dl by that, okay, we have to send in a reversible manner. Yes. Okay, this l we will send this side, and this y minus x to this side. So this will be dl by l is equal to 1 by y minus x into dx. Now this is equation 5. So now what happened? We will just substitute the limits to the extreme limits, integrating this equation 5 between two extreme limits. So extreme limits will be, so we are concerned our extreme limits in between the initial composition and final composition. Final composition will be residue, because in the residue concentration will be constant, whereas distillate concentration will be a variable, because of that only we are taking average. In each cut, the composition of more volatile component or the less volatile component will be very different, whereas in the residue it will be constant. Because of that, we are fixing our limits in between. When L is equal to liquid is L is equal to feed, so L moles is equal to F moles, then what happens to the more volatile component? So at L, the composition of more volatile is X, then at feed limits it is XF, it will become XF. Then when L is equal to W, when L is W residue, then what happens? So at L, X is the composition of more volatile component, then this X will become XW. Okay, between these limits we have to integrate that equation. That equation is dl by L is equal to 1 by y minus x into dx. So our limits will be, okay, any limit we can take. For example, f to w. So then these limits will be xf to xw, because when f is equal when L is equal to f, x is equal to xf. When L is equal to w, x is equal to xw. Or otherwise we can write this as like this one. So dl by L is equal to w to f. Then the limits we will have to interchange y minus x dx. The limits at w, L is equal to w, then the composition will be xw. When L is equal to f, the composition will be xf. So these are the equations. These equations are called Raleigh's equation. So this one we will give the equation number. This is 6. Equation 6 is called Raleigh's equation. Okay. So how to solve this Raleigh's equation? It's another criteria. For the problems we have to solve, usually we have to solve this equation. So the Raleigh's equation, how to solve this one? If you see, this is Raleigh's equation. DL, once again I am writing F2W is equal to integral dx by y minus x xf to xw. So if you see in the RHS side, this is integral. Okay, it is a complex one because y minus x is there. If you see, this is a simple. So we can just simply write this as ln L, integrate this one, then f and w is equal to integral xf to xw dx by y minus x. Then this will be upper limit minus lower limit ln f by w, w by f is equal to integral xf to xw dx by y minus x. Now any of the four quantities, like see, the quantities are here w, f, xf, comma xw. If we know any of the three quantities, we can automatically evaluate the other quantities. The unknown fourth quantity will be evaluated with this equation. But how to solve this equation? If volatility, so why the composition of more volatile component in the vapor phase is always dependent on its volatility. According to this equation, y is equal to alpha x divided by 1 plus alpha minus 1 into x. So y is always dependent on this volatility, relative volatility. Then if relative volatility is there, we have to input this y in this equation, then we have to integrate this equation. So usually what we will do to solve this equation, okay, there are three methods. There are three methods to solve this equation. To solve RHS. Okay, RHS of equation, Raleigh's equation that may be 6, equation 6. So how to solve this equation? One approach is we can just draw a graph. Draw graph between 1 by this y minus x versus x, this one. So this will be 1 by y minus x and this will be x. Draw the graph between 1 by y minus x and x. So this will be on y axis and this will be on x axis. And find area under the curve. Area under the curve. So it will be solved. So area under the curve between limits between xw and xf, whatever the graph it may be. So we have to take area between these limits only, xw and xf. Okay, this approach we can solve this equation. And another approach is Okay, and another approach is numerical integration. Integration using Simpson's one-third rule or trapezoidal rule. Okay, I hope you already done the numerical integration mathematical course. So these two rules are there in order to evaluate numerically the integral values. And the third approach is, if alpha is constant, then we can directly integrate equation 6. So Raleigh's equation directly can be integrated. If alpha is not constant, we have to apply one of these two methods, 1 and 2 method. If alpha is constant, we have to go for the integration method. So let's see how this integration method will looks like. For example, first method we will see how to evaluate this Raleigh's equation using first method. So first method is graphical integration, we will say. So if this is a graph, so x will be on this side and abscissa, and ordinate will be 1 by y star, or we can say y minus x or y star. So whatever the vapors are there, they are in equilibrium with liquid composition. That means y star minus x, or we can simply denoting it as y. Okay, both are same. Then whatever the curve will be there, in between curve will looks like this one. Okay, irrespective of whatever the points, the curve will looks like this one or the other shape. Then we will just denote what is our value of xw, and at other point we will denote what is our value of xf. So these points will be projected towards the curve. These 2 points will be projected until the curve. Then the area under this curve from xw to xf will be calculated. So area under the curve. So our Raleigh's equation will become ln w by f is equal to area under the curve. Okay, as a replacement for this integral, we are writing area under the curve. So the whatever the area under the curve value is there, just we have to equate with this ln w by f. So we can find what is the value of w, and since we already they have to provide f, then we can evaluate f is equal to d plus w. Using this equation, we can just evaluate what is d value. Then fxf, okay, we have to derive these two. Let's see, this is out of context now. So this one approach to solve the Raleigh's equation, and another approach is numerical integration using Simpson's one-third rule, or we can say second approach, numerical integration. So numerical integration, if you want a simple rule, okay, we can use a trapezoidal rule. Okay, because during the derivation of trapezoidal rule, they will assume the that integral as a first order polynomial. So if you consider a Simpson's rule, it is more advanced than the trapezoidal rule. The accuracy will be increased because they are assuming in their derivation as a integral as a second order polynomial. So if you see what is trapezoidal rule is nothing but whatever the integral are there. If you consider this as an integral from xw to xf to xw, or we can consider I is equal to xw to xf dx by y minus x. So whatever the points are there, so delta x into sum of the first and last point. Okay, first and last point plus sum of remaining points. Okay, you will solve one problem, then you will know how to do this one. Sum of remaining points, y points. Okay, remaining y points up to n minus 1. Up to n minus 1 remaining points, or otherwise we can use Simpson's 1/3 rule. Simpson's 1/3 rule, same integral is equal to xf to xw dx by y minus x is equal to delta x by 3. Since its denominator is 3, because of this only this is known as 1 by 3, Simpson's 1/3 rule. What this rule is saying, delta x by 3 is equal to sum of first 10 last ordinates. Okay, in the graph paper, if you see, the y-axis is called as a ordinate. Okay, x-axis is called as a abscissa, plus 4 times, or means 4 into 4 times odd ordinates plus 2 times even ordinate is called Simpson's 1/3 rule. So if you solve one problem using this one, it will be very okay for you. So you solve one problem, and the third method is, if relative volatility alpha is constant, we can directly integrate this one. So we already know what is that one. The Raleigh's equation is ln w by f is equal to integral xf to xw dx by y minus x. Then from equation y is equal to alpha x divided by 1 plus alpha minus 1 into x. So we have to substitute this here. So ln w by f is equal to integral xf to xw dx by y is alpha x divided by 1 plus alpha minus 1 into x minus x. So this one. So now what we will do, so ln w by f is equal to, we will take this one as a common. So xf to xw, so dx is there, and here, and in the extreme denominator we will take 1 plus alpha minus 1 into x as common. So this will be alpha x, and the next term will be minus x into 1 plus alpha minus 1 into x. So now we will send this extreme denominator to the numerator. So because a by b by c is equal to c by a, c into c, a into c by b. If you have any doubt, just see it. A by b by c is nothing but we can send it to the top. So ac by b. So same we have to apply here. ln w by f is equal to integral xf to xw. So this we are sending to the top, 1 plus alpha minus 1 into x divided by, so already dx is there, we are writing outside. Then this is alpha x minus, just okay, we will just one more step, x into 1 plus, we are expanding this one. So x we are sending out inside, so it will be alpha x minus x. This is, so this one, okay, for the convenience of operation I am taking this one outside. Okay, for solving, and then we will put there once again that one. So I am taking only this term outside. So 1 plus alpha, I'm just expanding this one, alpha minus x, alpha just sending inside. So alpha x minus x, this one, divided by alpha x minus, just I am expanding this term. So I'm sending x inside. So x into 1 x. So minus into plus is minus alpha x square. So minus into minus plus. So this will be x square. So this term, whatever term is there, this term, this one. So now what I am doing, so whatever this is there, so I'm just writing 1 minus x as separate plus alpha x, alpha x I am writing. Then from this term, if you see, there is x square here and there is x is there here. So x we will take common. So from these two terms, we'll take x common, then it will become alpha minus 1 minus, in this two term x square is common. So minus x square we will take common, x square into, so it will become alpha minus 1. Yeah, alpha minus 1. Then is it okay? Yeah, x square minus x square. Yes, it is okay. Then from this term, if you see, alpha minus 1, and in this also alpha minus 1 is common. So from these two terms, then we will do the operation 1 minus x, this is a one term, plus alpha x divided by, so we will take alpha minus 1 common from those two terms. So x minus x square it is. So x minus x square. So if you see this one, we can write 1 by alpha minus 1 outside, this one we will take outside. Then whatever the values are there, 1 minus x plus alpha x divided by, so this x minus x square we can write like this, 1 minus x into 1 minus x. So this will have an advantage. So is equal to 1 by alpha minus 1 into, so just we are dividing with each term, denominator with each term, 1 minus x. So first term it will be x into 1 minus x, and for the next term it is alpha x divided by x into 1 minus x. Here if you see, x and x we can cancel out. Here 1 minus x and 1 minus x can be cancelled out. So now it will be 1 by alpha minus 1 into, here only 1 by x is left, plus here only alpha by 1 minus x is left. So this is the term. The term is equal to whatever the term we are taking, that term. So this term we need to substitute over there. So this whole term, whatever we obtain, we need to substitute here. So into dx. Okay, we should give some equation numbers so that it will be very easy. So this is Rayleigh's equation. Already we have given this as a 6. So this will be from the top. We should be, for the Rayleigh's equation we have given as equation 6. Then from trapezoidal rule we will give 7. This trapezoidal rule will give equation 7, and Simpson's rule will give equation 8. Then this will be equation 9, y value, and this equation 9, and after substituting in this equation 9 in, substitute equation 9 in equation 6, which is Raleigh's equation. Then this will be equation 10 after substituting y value. Then we will obtain this term. So this will be 11, we can say. So substitute whatever the term we obtain in the equation 11. So substitute this term in equation 11. So equation 11, what it is saying, ln w by f is equal to, so in place of that term we are substituting alpha minus 1 into 1 by x plus alpha by 1 minus x, which is dx. So this is integral xf to xw. So xf to xw, that one. So now already we assume alpha is constant. So we can take it from the integral 1 minus alpha, then this will be xf to xw 1 by x dx plus alpha by 1 minus x dx. Just integrate, a simple integration. This is ln w by f is equal to 1 by alpha minus 1. So this will be ln x whose limits are, so it will be in a bracket, whose limits are from xf to xw plus this integral of this one is, this is also we are writing integral one more time. So xf to xw. Integral of alpha is already constant, so we can take this one. So this one will be minus ln of 1 minus x. So the integration of this equation is that one. So limits are xf to xw. Then we will substitute the limits. So limit substitution is upper limit minus lower limit. 1 by alpha minus 1 into, so this is upper limit minus lower limit, we can write. So this one is ln xw minus ln lower limit xf plus, so this minus is there, we can take this minus outside. So now we can write ln 1 minus upper limit xw, then next one is okay plus, let us not substitute the plus sign. So this will be minus upper limit minus lower limit. So minus minus will become plus, then it will be 1 minus xf. So xf. So then the final equation will be ln w by f is equal to 1 by alpha minus 1. So here if you can write ln, this is in the form of ln a minus ln b. So we can write this as, solution will be ln a by b. So this is formula. By formula we can write ln xw by xf. Then we can take minus common. So minus alpha is there. Okay. So okay, here alpha is there. Already alpha is there. So here if you see, alpha will be there here and alpha will be there here. So alpha we can take common. So alpha ln. So minus we have taken common. So we will obtain this as 1 minus xw divided by 1 minus xf. So this is the solution for Raleigh's equation when alpha is constant, relative volatility is constant. I am writing clearly once again this one. Ln W by F is equal to 1 by alpha minus 1 into ln xw by xf minus xf alpha ln 1 minus xw by 1 minus xf. So this equation is the Raleigh's equation, solution for Raleigh's equation if alpha is constant. Solution for Raleigh's equation if alpha is constant. Okay, alpha is relative volatility. This one, if you have any doubt, you can ask me. Otherwise, I will quickly move to the problems. Anybody is having doubt? Or shall I move? Yes.
Continue, sir.
Okay. Yeah. Thank you. Okay, let us solve the problem. So if you solve one problem, then you will understand. So all the three approaches I am going to discuss, all the three methods of solution. So this is the problem from your old question paper. So 100 moles of benzene, just pasting there. Okay, yeah. If you see, this one is the problem. So here, what they are saying, 100 moles of benzene. So 100 moles of benzene. This one is 100 moles of benzene, which is they are stating this is component A. So benzene is a more volatile component. In a mixture of toluene and benzene is there, in which A component A is benzene. Then obviously the component B will be toluene, containing 50 mole percentage of benzene. So this is XF. So this is F. This is XF 50 mole percentage benzene is subjected to a differential distillation. So this is important. So how the distillation has been carried out, whether it's a flash distillation or continuous or a differential distillation. So this is differential distillation, meaning it's a simple distillation at atmospheric pressure. So pressure, total pressure will be 1 atm till the composition of benzene in the residue. Okay, this is XW. So residue is 33 percentage. Okay, they are carrying out till the composition in the residue, composition of benzene in the residue is 33 percentage, from 50% to 33 percentage. Then the operation is carried out. Calculate the total moles of mixture distilled. Okay, total moles of mixture distilled, that is D we have to calculate. Then average relative volatility may be assumed as 2.16. So this is constant relative volatility. So now we'll solve this one. So this one, if you see, the given data is, so given data is F is equal to 100 moles. Then 50 percentage of the F is benzene. So benzene is a more volatile component. We can take as 50 percentage, which is 0.5. Then is subjected to a differential distillation at atmospheric pressure till the composition of the benzene in the residue is 33 percentage. XW is equal to 0.33. Calculate the moles of the mixture distilled. They are asking to calculate what is D. Then alpha they have given alpha is equal to 2.16. Okay, for the convenience or for the understanding, better understanding, I am going to solve the equation of Raleigh's using all the three equations, all the three methods. So let us assume first we will solve this problem using the graphical approach. So if you see this one, the distillation operation has to take place from 0.5 initially the benzene to 0.33 at the output of the benzene. So if you see this one, X composition in liquid phase X, and other one is Y we have to calculate. Then next one, according to Raleigh's equation, since this is a differential distillation, the Raleigh's equation is ln W by F is equal to integral xf to xw dx by y star minus x or y minus x. So x and y we needed to evaluate this integral, w and f we needed. So we don't know what is w here. So without w we can calculate, since the mass balance. Okay, I forgot to conduct a mass balance. Just differential approach I just given there. So this is a solution of Raleigh's equation. Then if you see the simple distillation unit, this is differential unit. So if you see this one, here F moles are going inside and D moles are coming outside, along with W moles of residue it is coming outside. So the mass balance for this distillation column, overall simple distillation column, is we can write F is equal to D plus W. Okay, you might have seen this equation earlier also. So the mass balance or the mole balance is F is equal to D plus W. Then the component balance will be, for mole volatile component, is F into XF is equal to D into YD average, because it's a simple distillation. So cuts will have different composition. So this is XWW. So these are two equations which I have left earlier during the derivation. So these two equations is used after evaluating. When they said in the problem is a differential distillation, means first you have to evaluate Raleigh's equation, then you have to go to this material balance equation, then you can evaluate whatever the D or W, whatever you want. So in the problem, first we have to evaluate the Raleigh's equation. So this one is Raleigh's equation. So in this Raleigh's equation, what we are known, this is already known, F is already known, and XW is known, and XF is known. But we don't know what is the value of W. So we can directly calculate using the graphical approach. First method is graphical approach. So graphical approach we are going to calculate. So X and W we need at each interval, and together with that one. So according to this equation, graphical approaches, we need to get 1 minus 1 divided by y minus x. So x values, how can we fix out? So distillation operation has to carry out from 0.5 to 0.33. So if you write this as 0.33 residue composition, this is xw. Then we will slightly increase these values up to 0.5. So for example, 33 points, let us say this is 0.36. Okay, in between values we can assume up to 0.5. We have to just adjust these values from 0.33 to zero point 0.5. So if you take point, this is 0.39. The difference between any 2 points will be 0.03. 0.33 is, this is XW, then 0.36, then this will be 0.9452, 0.42, then this will be 0.43, then this will be 0.46, okay, 45. 0.03.45 plus 3 is 5, 6, 7, 8. Then last one is 0.4. Okay, this one will be XF. So XF to XW, we have to adjust the values. 4, 5, 4, 8. Okay, no problem. This is. So now y value we have to evaluate. How can we evaluate y value? We already know what is y value. Y is equal to alpha x by 1 plus alpha minus 1 into x. So using this value we can evaluate what is y. So alpha we already know it is 2.16. They have already given. So for the first value you can take this as 0.33 divided by 1 plus alpha is 2.16 minus 0.33. So you can calculate this value and put here. Can anybody say what is this value?
Sir, 0.515, sir.
515. Okay, similarly for the next value also we can calculate. So for the next value this is 0.1, and for 0.2 y is equal to alpha is equal to 2.16 into 0.36 divided by 1 plus 2.16 minus 1 into 0.36. So this value also you can calculate. Okay, using this formula you can calculate the y values. Then using this x and y values you have to calculate these values. Okay, let us continue this in the next class. Okay, for the next class the task is to complete this table. Entire table you have to calculate using your calc whatever the values, and in the next class just say me what are these values. From there onwards we will continue these values. Okay, if you have any doubt you can ask me. If you want anything extra class I can also take. Okay, do you have any doubts?
No, sir.
Okay, let us stop here. Thank you for listening.